And last section in this chapter is about why real gases aren't perfect, because you're all perfect, right? So anyways, we talked about the ideal gas equation, and we know that you can use that for basically every situation unless you're like working for NASA or in deep sea or whatever. But realistically, there is no gas that is ideal. The ones, some are closer than others, but basically there's two situations when gases misbehave. The first situation is high pressure. The second situation is low temperature. So if you would go to, say, Jupiter, that is basically the best situation for when gases misbehave, because Jupiter is super huge, so it has a lot of pressure, and it's very far from the sun, so it has low temperatures, which is why, if you think of it, it's a gas giant and has lots of weird things like the giant red spot. But those are the two situations that they misbehave on average. Why don't they behave? Kinetic molecular theory is the reason. And again, what we talked about before is that we assume that molecules don't occupy any space and they have no attractions. Like we assume that gas molecules are basically islands amongst themselves. They don't know that any other molecules exist, but that's not true. Real gases, and remember, every gas is real. We're not in the imaginary world. They do take up space. They do have a small amount of volume, and they do have attraction. So if gas molecules get really close to each other, they're going to start seeing these. So a big thing here, when pressure increases, all of a sudden the gas molecules get closer together, so they have attractions. And when you're really, really squished, the amount of volume you take up, the space you take up, comes into play. When your temperature decreases, that's when you're getting to the point where either you're liquefying or you're actually skipping it completely and doing deposition where you go right to a solid. So what happens is the attractions begin to become important again a lot. So that's why those two situations are when they misbehave. And again, this is just showing you here we have low pressure. The gas molecules are fairly far from each other, whereas over here we have the piston compressed and we have a lot of pressure going on here. And again, this is when they would misbehave more than over here. So what do? We have ways to get around this. One is the van der Waals equation. You don't need to do van der Waals on the AP test or anything, but you should know that it exists because you're an educated person. So there's engineers and scientists use it the most, and they use it when the ideal gas law doesn't work. So when you're working for NASA, when you're doing submarines, when you're building aircrafts, when okay is not good enough. And what we have is van der Waals came up with it, obviously, and you have two constants. Each gas has its own constants. The first one is basically how attracted are the molecules to each other. So the bigger A is, the more attraction there is. And B is literally how big the gas molecules are. And here's the equation for that, which is very nice. You can see if you take out this section and this section, you do just have PV equals nRT. So these are just the extra things right here. The chart just shows you the different A's and B's. So you can see that carbon tetrachloride has the largest attraction. It's kind of freakishly attracted to itself. And over here you can see the volume of things, and you can see carbon tetrachloride is the largest gas as well. It takes up the most space per mole. And then this equation here is just showing you, okay, if we do one with the ideal gas law and we do one with van der Waals, this is not a large difference, but even here, we're only at 300 Kelvin and we're only, 2 liters. This is actually just like normal room temperature, and there's already a noticeable difference. So again, if you're going to, say, Mars, and you would want someone to use van der Waals equation to figure out your stuff as opposed to an ideal gas law. So I hope this makes gases a little more clear, and I hope that you do really well on your tests.